Neptune, the eighth planet from our Sun, is a breathtaking blue giant. It's a realm of icy clouds and supersonic winds, a world vastly different from our own. This gas giant, named for the Roman god of the sea, holds a special allure for astronomers and space enthusiasts alike. One of the most captivating aspects of Neptune is its family of moons. 14 moons are known to grace Neptune's celestial neighborhood, each with its own unique story to tell. These moons range in size and shape, offering a diverse collection of celestial objects for scientists to study. Some moons are covered in craters, evidence of a long history of impacts. Others have smoother surfaces, possibly shaped by geological activity. Scientists believe these moons hold valuable information about the history of our solar system. Among Neptune's 14 known moons, there's a diverse cast of characters. Triton, the largest, is a world of icy volcanoes and nitrogen geysers. Proteus, the second largest, has a unique, irregular shape that hints at a violent past. Nereid, another notable moon, has one of the most eccentric orbits in the solar system. Despina and Galatea, for example, play a crucial role in maintaining Neptune's ring system. They act as shepherds, their gravity confining the ring particles and preventing them from spreading out. Studying these smaller moons provides insights into the delicate gravitational balance that governs planetary systems. The moons of Neptune, large and small, offer a fascinating glimpse into the diversity and complexity of our solar system. One of these intriguing moons is Larissa, a small dark world that orbits Neptune in a tight embrace. Larissa, named after a lover of Poseidon in Greek mythology, is a moon shrouded in mystery. Discovered in 1981 by its subtle effect on starlight, Larissa remained a mere blip in our understanding of Neptune's system for years. It wasn't until Voyager 2's flyby in 1989 that we got our first close-up glimpse of this enigmatic moon. Larissa's surface, scarred by countless impacts, tells a tale of a moon caught in a cosmic crossfire. These craters offer a window into the history of our solar system, a record of the countless collisions that have shaped our cosmic neighborhood. Despite its small size and seemingly desolate landscape, Larissa holds a certain allure. Larissa's story begins with a subtle flicker of light. On May 24, 1981, a team of astronomers, led by Harold Reitzemer, were observing Neptune. Their goal wasn't to find new moons, but to study Neptune itself. However, as they meticulously analyzed the data, they noticed something peculiar. There was a slight, almost imperceptible dip in Neptune's brightness. This dip, they realized, could only mean one thing. An object was passing in front of the planet, momentarily blocking its light. This object, they soon determined, was not a known moon. The faint flicker of light provided only tantalizing hints about this newfound moon. Harold Reitzemer, the astronomer who spearheaded the team that discovered Larissa, was no stranger to the outer solar system. He had already made significant contributions to our understanding of these distant worlds. His expertise in planetary astronomy and his meticulous observational skills made him the ideal leader for this groundbreaking research. Reitzemer's interest in the cosmos began at a young age. He was captivated by the stars and driven by an insatiable curiosity to unravel the mysteries of the universe. This passion led him to pursue a career in astronomy, where he quickly made a name for himself as a skilled observer and a meticulous researcher. His work on the outer solar system was particularly noteworthy. Reitzemer's discovery of Larissa, while serendipitous, was a testament to his dedication and expertise. The method used to discover Larissa, known as occultation, has been instrumental in uncovering many celestial objects. It's a technique that relies on patience, precision, and a bit of cosmic luck. Occultation occurs when one celestial object passes in front of another from our perspective on Earth. This passing causes a temporary dip in the brightness of the more distant object, a subtle signal that astronomers can detect with sensitive telescopes. The duration and depth of this dip provide valuable information about the size and shape of the occulting object. In the case of Larissa, the occultation was brief, lasting only a few seconds. The discovery highlighted the power of occultation as a tool for exploring the solar system. For years after its initial discovery, Larissa remained little more than a blip in our understanding of Neptune's system. The ground-based observations, while groundbreaking, could only reveal so much. That opportunity came in 1989, when Voyager 2 made its closest approach to Neptune. As Voyager 2 hurtled past Neptune, it captured a series of images of Larissa. These images revealed a dark, heavily cratered world, a testament to the countless impacts it had endured over billions of years. The Voyager 2 flyby was a fleeting encounter, but it provided a wealth of information about Larissa's size, shape, and surface features. It transformed our understanding of this distant moon, from a faint flicker of light to a real world with a story to tell. Voyager 2's flyby past Larissa in 1989 finally gave us a good look at this mysterious moon. The images revealed a world that is small, even by moon standards. Larissa measures roughly 120 miles across, about the size of a small country. This small size has a significant impact on Larissa's gravity. The gravitational pull on Larissa is far weaker than what we experience on Earth. Its small size and weak gravity suggest that Larissa is in many ways more similar to an asteroid than to a large moon like our own. The images beamed back from Voyager 2 showed a world that has been heavily bombarded throughout its history. Larissa's surface is heavily cratered, covered in impact scars of all shapes and sizes. These craters are a testament to the moon's long and violent history, a silent record of the countless collisions it has endured. Some of these craters are enormous, stretching for miles across the surface. Others are much smaller, mere pockmarks on the moon's already battered face. Unlike some moons in our solar system that show signs of geological activity, Larissa appears to be geologically dead. While we can glean much from images, understanding Larissa's composition requires a closer look at the light it reflects. Scientists use a technique called spectroscopy to analyze this light. The data collected so far suggests that Larissa is primarily composed of water ice mixed with darker materials. The exact nature of these darker materials is still uncertain, but they are likely a mixture of rock and carbon-based compounds. Further study of Larissa's composition could provide valuable insights into the conditions that existed in the early solar system. Unlike many larger moons that are spherical, Larissa has an irregular shape. It's more like a lumpy potato than a perfect sphere. This irregular shape is likely a result of Larissa's small size and its violent past. Smaller celestial bodies, lacking the strong gravity of their larger counterparts, don't have the same gravitational forces to pull themselves into a spherical shape. Over time, the countless impacts Larissa has endured have further sculpted its shape. This irregular shape has implications for Larissa's rotation, thought to tumble chaotically as it orbits Neptune. Larissa orbits Neptune at a distance of about 45,000 miles closer than our own moon orbits Earth. This close proximity means that Larissa is tightly bound to Neptune's gravitational pull, completing one orbit in just under 13 hours. Imagine that. A whole year on Larissa whizzes by in less than a day on Earth. Larissa isn't just orbiting, it's racing around the planet in a celestial ballet governed by the laws of physics. Larissa's orbit is not perfectly circular, but slightly elliptical. This means that Larissa's distance from Neptune varies slightly throughout its orbit. While Larissa's current orbit is stable, it faces a long-term threat: orbital decay. This phenomenon, driven by the subtle but persistent forces of gravity, is slowly but surely causing Larissa to spiral inward towards Neptune. The primary culprit behind this orbital decay is tidal friction. Just as the Moon's gravity creates tides on Earth, Neptune's gravity creates tides on Larissa. This misalignment creates a slight torque on Larissa, acting like a brake on its orbital motion. Over vast stretches of time, this braking effect causes Larissa's orbit to shrink, bringing it closer and closer to its eventual demise. As Larissa spirals inward, the tidal forces acting upon it will become increasingly intense. These forces, arising from the difference in gravitational pull across Larissa's diameter, will literally stretch and squeeze the Moon. This tidal stretching will generate heat within Larissa's interior, potentially melting some of its icy constituents. One possibility is that it will eventually break apart under the strain of these tidal forces, forming a ring of debris around Neptune. Another possibility is that it will remain intact, ultimately colliding with Neptune in a cataclysmic event. Regardless of its eventual fate, Larissa's story is a poignant reminder of the power of gravity and the ever-changing nature of our universe. The possibility of Larissa forming a ring around Neptune is particularly intriguing. Neptune already possesses a system of faint rings, but they are much less prominent than the majestic rings of Saturn. If Larissa were to break apart, the resulting debris field would spread out over time, potentially creating a new ring around Neptune. This ring, while initially faint, would gradually become more prominent as it was replenished by the ongoing disintegration of Larissa. By analyzing the light reflected by the ring particles, scientists could learn more about the materials that make up this enigmatic moon. The potential for Larissa to contribute to Neptune's ring system highlights the interconnectedness of celestial objects and the ever-evolving nature of our solar system. One of the intriguing aspects of Larissa, and indeed many moons in our solar system, is its synchronous rotation. This means that Larissa takes the same amount of time to rotate on its axis as it does to complete one orbit around Neptune. As a result, Larissa always shows the same face to Neptune, just as our moon always shows the same face to Earth. This phenomenon is a consequence of tidal forces, the same forces that are slowly causing Larissa's orbit to decay. Over millions of years, these tidal forces have gradually slowed down Larissa's rotation until it reached a state of equilibrium where its rotational period matched its orbital period. This synchronous rotation has a profound impact on Larissa's environment. It means that one side of Larissa is perpetually bathed in sunlight, while the other side is shrouded in perpetual darkness. This stark contrast in illumination likely leads to extreme temperature differences between the two hemispheres. Larissa, a dark world in the outer solar system, has a very low albedo. Albedo measures how much light an object reflects. Larissa's albedo is around 0.09, reflecting only 9% of sunlight. This makes it difficult to observe from Earth. Scientists believe dark organic compounds or fine-grained material could be the cause. While Larissa's surface is undoubtedly a cold and barren place, there's a tantalizing possibility that a much warmer and potentially habitable environment exists beneath its icy exterior. Scientists believe that Larissa, like several other moons in the outer solar system, could harbor a subsurface ocean of liquid water. This ocean, if it exists, would be located beneath a thick layer of ice, kept liquid by a combination of heat from Larissa's interior and the tidal forces exerted by Neptune. The heat generated by tidal forces is particularly important in maintaining subsurface oceans in icy moons. The presence of a subsurface ocean on Larissa would have profound implications for our understanding of the potential for life beyond Earth. On our own planet, we find life wherever we find liquid water, even in the most extreme environments. If Larissa does indeed harbor a hidden ocean, it would join a growing list of worlds in our solar system that could potentially support life. While Voyager 2's flyby provided invaluable insights into Larissa, it left many questions unanswered. To truly unravel Larissa's secrets, we need a dedicated mission to this enigmatic moon. Such a mission, equipped with modern instruments, could revolutionize our understanding of Larissa and its place in Neptune's system. A future mission to Larissa could involve a combination of remote sensing and in situ measurements. A spacecraft could orbit Larissa for an extended period, mapping its surface in high resolution, studying its composition in detail, and characterizing its magnetic and gravitational fields. A lander could touch down on Larissa's surface, collecting samples of its icy regolith and analyzing them for signs of organic molecules or other evidence of past or present life. Such a mission would be a challenging undertaking, requiring advanced technology and a significant financial investment. However, the scientific rewards of exploring Larissa, a world that holds clues to the formation of our solar system and the potential for life beyond Earth, would be immeasurable. Larissa, despite its small size, offers a profound glimpse into our solar system's workings. This tiny moon, orbiting Neptune, is a relic of the early solar system. The heavy cratering on Larissa speaks of a chaotic early solar system. Studying those craters helps scientists infer the history of impacts on Larissa. Impacts have delivered materials, potentially even organic molecules. Larissa's composition, primarily water ice, is typical of outer solar system objects. Studying Larissa's composition sheds light on the early solar system's evolution. Small worlds like Larissa hold immense scientific value. Once considered mere bystanders, they are now seen as crucial. Small worlds are diverse in compositions and histories. They hold clues to our solar system's formation. Larissa, with its potential subsurface ocean, is crucial. Life may exist in environments like Larissa's. Exploring a world like Larissa, while scientifically compelling, presents significant technological hurdles. Its vast distance from Earth, coupled with its small size and faintness, makes it a challenging target for observation and exploration. A dedicated mission to Larissa would require advanced spacecraft capable of long-duration voyages, equipped with sensitive instruments designed to operate in the cold, dark environment of the outer solar system. Landing on Larissa and penetrating its icy shell to explore a potential subsurface ocean would be even more challenging, requiring innovative technologies and considerable engineering ingenuity. However, the scientific rewards of such a mission would be immeasurable. Imagine the knowledge we could gain by analyzing the composition of Larissa's surface and by studying its interior structure, and by searching for signs of past or present life in a potential subsurface ocean. Such a mission would not only revolutionize our understanding of Larissa, but also provide invaluable insights into the formation and evolution of icy worlds throughout the universe. The exploration of space, particularly the exploration of distant worlds like Larissa, has a profound impact on humanity that extends far beyond the scientific discoveries themselves. It inspires us, ignites our imaginations, and reminds us of the vastness and wonder of the universe we inhabit. When we invest in space exploration, we are investing in the future. We are pushing the boundaries of human knowledge and inspiring future generations to pursue careers in science, technology, engineering, and mathematics. These are the fields that will drive innovation, solve global challenges, and shape the future of humanity. The story of Larissa is far from over. It's a story that's still being written, a story that will continue to unfold as we develop new technologies and send new missions to explore the outer reaches of our solar system. As we continue to explore, we can be certain that Larissa and other small worlds like it will continue to surprise us, challenge our assumptions, and deepen our understanding of the cosmos and our place within it.